So hello everyone, this is lecture 30 for the quantum mechanics. In the last lecture we have started the applications of quantum mechanics, and I was telling you about the potential barrier, potential step and the particle in a box. So we'll start with the potential step and we'll discuss everything. So let's start. What is potential step? So when you are moving in some area, then there is nothing potential, means there is zero potential here, and you will see that there is some barrier, and you need to increase your energy to pass through that. So it is something like a step, means after this the potential will remain constant, but it is higher than where you were previously. So if it is remain constant forever, then it will be like potential step. And now what is the difference between potential step and potential barrier? If this will, after some time it will reduce to again to the same value, then you will call it as potential barrier. So I can give you the example. So it's like there is a charge ring which is 10 volt, and you have a proton which is have 20 electron volt energy. So it can pass through this, but see, when it approach this ring of the positively charged, then its potential repulsion will increase, that will give a barrier to it. So after that, when it pass through this, it will again reduce. So it is like act as the potential barrier for this. But if it remain constant, like we can take an example of this circuit. So there is this resistance, and if there is this proton, and then for this proton there will be always be this potential remains same for this complete path up to this battery. So that's how this is the example of a potential step, and this is the example of potential barrier. So I hope it is clear to you. Now we can define this potential step as it will remain 0. We will define this position as x equal to 0 where this step is came. So it will be 0, potential is 0 when it is less than x0 in all this region, but it will become v0 when it is s is greater than 0, means it will remain v0 here. Now see, if the energy is E, then up to here this will remain E, and we'll say that it is completely kinetic energy. But when this potential came, then this total energy, means net kinetic energy, will be reduced, because E minus v0 will give you kinetic energy. Now if kinetic energy is reduced, then we know that momentum is related to the kinetic energy, so momentum will also be reduced from the initial value. So that's how we will see that how that will affect the equation of the quantum particle. So if particle is far away from x equals 0 toward x is negative, this side, it is free, but it will experience repulsion potential when it approach x equal to 0. And for x less than 0, momentum is nothing but under root 2me, because we know kinetic energy is equal to p square by 2m. So from there you can find p equal to root 2me. But for the x greater than equal to 0, this will be total kinetic energy will be E minus v0. So p will become under root 2m E minus v0. So this is your momentum, how it is defined for these two spaces. So we will consider two cases. First we will say that energy of the particle is greater than this v0, and then we will discuss the case when the energy is less than v0. So first let's discuss the case when it is greater than v0. So we know quantum mechanically, first what happens classically. If we see this thing classically, then we will know that particle is coming, and after this kinetic energy will reduce, momentum will reduce, and that's how things will go in the classical mechanics. But what is the difference in the quantum mechanics? So let's see. To solve in the quantum mechanics, we know what we do. There were steps I told you, that first we will write the Hamiltonian, then we'll write the time independent Schrodinger equation, and we'll find the eigenstates. So first the Hamiltonian will be p square by 2m plus vx, this is your total energy. And the second one is write the Schrodinger's time independent equation, so this is your time independent equation. Now for the, when we consider that it is E is greater than v0, and then there will be two reasons. First, x less than 0 and x greater than 0. For x less than 0, potential is 0. So Schrodinger equation for x less than 0 will become, this term will be 0, and this will go this side, so it will give you this d square psi by dx square plus k1 square psi equal to 0. So this is your first equation, means this will be your equation. Now we assume 2me by h cut square as k1 square. So this is your equation 1 for the x less than 0. Now for x greater than 0, the energy will become E minus v0 here, and this will become v0, means this is E and this will become v0. When this term will go to the right side, it will become E minus v0, and this is again plus. So equation, the means Schrodinger equation will become this: v equal to v0 d square psi by dx square plus 2m by h cut square, my E minus v0 psi equal to 0. So these are your two equations. Now again we will assume this as k2 square. So we will have these two equations, first and the second. Then we will use the mathematical physics to solve the differential equations. So you know already that how to solve the differential equations, that is d square plus k1 square equal to 0. That's how we can find the solution. So let's find that. So first equation will change to this, and this is your second equation. That was your k1 square with, that was your first equation. So first equation will give you d square plus k1 square psi equal to 0. From here d is nothing but plus minus iota k1, and for the second equation, this one d square plus k2 square, this is will give you d equal to plus minus iota k2. So solution for first equation will become exponential iota k1x plus b exponential minus iota k1x. So how this solution is came, you must see the differential equation solutions in the mathematical physics, so you will know how we write this solution. So we just solve that differential equation using the mathematical physics and we'll get this solution. Using this, we'll just put a exponential I lambda 1x and lambda 2. So this will give you this. Now for x greater than 0, the solution will be c exponential iota k2x, because this time it is k2. So you will get these two solutions. Means this is your wave function before x greater than 0, and this is your wave function after it is passed to the x equal to 0, greater than 0. Now see, here you will see when particle is in this area, so there is wave is coming towards this barrier and also reflecting from this. So there you have the two solutions possible. That's why these both terms will be in the picture. Means this represent that wave is going in the forward direction. You remember from the EM class, that is kx minus omega t, we understand in the EM waves, and when it is minus kx minus omega t, then it will going in the opposite direction of that z. So that's how you can just determine that what will be the direction of the wave. So if it is plus k1x, that will give you positive direction, and it is minus k1x, means it is going in the negative direction. So this is your incidence wave and this is your reflected wave for the first wave function and first wave function in this. So that's why we can define both these waves. But here this, in this region, there is no reflected wave, so only one component is required, which is going forward. That's why we will just neglect this term and this will be 0, because there is only forward going wave. So this will change to c exponential iota k2x. So these, now we have these two solutions for the x less than 0 and x greater than 0, these two terms and this only one term. Now this is your wave function, so we have find the wave function. Now this is nothing but this is your eigenstates for the first wave function, before that and after that this is your wave function or the eigenstates. So you have the eigenstates. Now what we need to find, first let's see the probability of the particle before x means before x equal to 0 and after x equal to 0. So how we find the probability? If we know the wave function, we just need to find the mode of a wave function, that will give you probability, means square of mode. So how to find the mode square? If the number is complex, then you find the mode by just multiplying the conjugate. So this square will be given by the psi1 conjugate and the psi. So for the first one, just to find the this one, and the conjugate will give you minus iota k1x and plus iota k1x. So we just multiplied them, and after solving this you will get this term, a square plus b square plus 2ab exponential 2 iota k1x plus exponential minus 2 iota k1x divided by 2. And now this term is nothing but cos iota k, means cos 2kx 2k1x. So this will reduce to this. Now see, this probability is a periodic function, means it is a sinusoidal wave, means probability is also oscillating. So that's how, if we plot the probability, this will came out to be this before x equal to 0, and if we find the probability after passing that x equal to 0, that will give you mod of this. So this will give you c square. After solving this you will get c square. So means probability will remain constant after passing through that. And what this means how this probability is fluctuating before the x equal to 0. So because when the wave is coming from here, then there is coming wave and the reflecting wave. So both waves will interfere, and interference will give you the change in probability. Means because of the interference you will get somewhere the high probability, somewhere the low probability. So because of these two waves we are getting this kind of situation, but after that we have only one wave, that's why we are getting the constant probability. So I hope it is clear to you the probability. Now we are having this transmission wave and we are having incidence wave and reflecting wave. So we need to find the coefficients, means reflection coefficient and the transmission coefficients. So we know how to find them, we already studied in the EM waves. So that is the same thing we will apply here. To find the reflection coefficient, is nothing but reflected current density divided by incident current density. So whatever the, if the wave is here, means it is coming here, and it can pass through this also, transmit also. So we are now assuming, means this was the solution, so we studied this. Now we are seeing that if any wave is coming and it is reflecting and transmitting, so what is the reflection coefficient? Means that will be incident wave intensity, and that will divide the reflected wave density or the current density. So and here the current is nothing but, this is the probability current density, means this is not the charge current anything, this is just the particle density you are finding. So this will be J reflected and divided by J incident, this will give you reflection coefficient. And now here we will use the same equation of continuity we have derived in the EM waves. So this was your equation of continuity, del dot J equal to minus del rho by del T. And in the EM waves or the electricity and magnetism, we have seen that this is nothing but charge density, this is your current density. So in this quantum mechanics, what this represent? This represent the probability density This is probability density of the particle, and this J represents the probability current density. So that's how we define this equation in the quantum mechanics. So we will use this, and because we need this J reflected and the J incident, that's why we'll use this. So this rho is nothing but probability density, and if you just multiply with the dV, you will get the probability of finding the particle in the volume dV. So this is nothing but probability density. You need to remember this, that this is your probability density. This J is nothing but probability current density. So, and from this equations we get this expression for the J. So only you need to remember this expression. So J can be found by h cut by 2im, and this is psi star del d psi by dx minus psi del psi star by del x. So this formula will give you J, and you will substitute J here, and you will find the reflected coefficient, and you will find the transmission coefficient. So J reflected is given by, means for the reflected wave we have seen here, this is your eigenstate. So this will be this b exponential minus iota k1s. This is the reflected one. So the psi star of this will give you means plus iota, and the psi will give you minus. So we'll use this. So J reflected is nothing but h cut by 2im phi 2 star and del phi 2 by del x, phi 2 star by del x. So in place of phi 2 you have this complete term b exponential minus iota k1x, and when it is phi, means for this first wave you have phi 1 and phi 2. This is your phi 1, this is your phi 2. For second wave you have this phi 3 only. So we'll use this to find the J. So for the reflected one, this is your phi 2 star phi 2. So you will just find the differentiation of this. So phi 2 divided by del phi 2 by del x will give you something, and phi 2 star will give you plus iota k1. So just multiply them, and just substituting these values after taking the differentiation will give you this term. So you can easily find this derivative from the help of phi 2. This J reflected will be minus mod of b square h cut k1 by m, and similarly you will find the J incident. Now for the incident you will use this phi 1. So this is a exponential iota k1x. This is the incident wave. So the phi star will give you exponential minus iota k1x, and you can find this. So for the incident wave you will get h cut by 2im phi 1 star. This will give you mod a square h cut k1 by m, and similarly you can find for the J transmitted. So J transmitted will be given by this. This is your phi 3, and this you can find the phi 3 star. You can find the del phi 3 by del x using this, and just substitute the values, and you will get this expression mod c square h cut k2 by m. Now you have all the three current densities, or the probability current densities. So you can find the reflection coefficient and the transmission coefficient. So for the reflection coefficient, this is nothing but reflected divided by incident, and for transmission it is nothing but transmitted divided by incident. So we'll just take the ratio. So it is this divided by this will give you b by a square, and we need to take the mod. So we'll get this b by a square for the reflection, and for transmitted we'll get J transmitted divided by J incident. So this divided by this will give you c by a square, and this will give you k2 by k1. So this is your transmitted coefficient, and this is your reflection coefficient, and always remember this r plus t will always give you 1. Now we have these variables c, a and b. So we need to find these variables also. So for that we will use the boundary conditions. So for this interface, this is your interface when it is striking. So at the interface you will see that wave function will be continuous, and the differentiation of the wave function will also be continuous. So if we put x equal to 0, then phi must remain same, size must remain same, and differentiation of psi del psi by del x must remain same. So psi 1 x equal to 0 must be equal to psi 2 x equal to 0. So from here we just substitute the value at x equal to 0. It will give you a plus b, and this will give you c only. So a plus b must be equal to c. This is your first equation. Now for the second equation you will find the differentiation. Del psi 1 by del x must be equal to del psi 2 by del x at x equal to 0. So find the differentiation, and you will get this equation k1 a minus b equal to k2c. Now using these two equations we will find the value of a, b and c. So means we can just find the ratio, because these are three variables and we have only two equations. So b by a will be came out to be k1 minus k2 by k1 plus k2, and c by a will be 2k1 by k1 plus k2. So from here we can find this ratio. Now only we need the ratio only here to find this means reflection and the transmission coefficient. So that's why we'll use this. So b by a is this. So square of this will give you reflection coefficient. So this will be your reflection coefficient, and now the transmit coefficient will be c by a is this. So square of this and multiply k2 by k1. So this will be your transmission coefficient. Now here we can just take the k1 common. So it will give you 1 minus k2 by k1. Here also take k1 common. It will give you 1 plus k2 by k1. K1 cancels out. So you will just assume k2 by k1 as alpha. So this will be your 1 minus alpha 1 plus alpha square, and here also assume k2 by k1 as alpha. You will get 4 alpha divided by 1 plus alpha square. So this is your reflection and transmission coefficient, and now alpha is k2 by k1, and we assume that k2 is nothing but, so we assumed here. So this was your k1 under root 2m e by h cut, and k2 was under root 2m e minus v naught divided by h cut. So if you take the ratio k2 over k1, then this h cut will cancel out, and you will get this ratio 2m e minus v naught divided by 2m e. So this will cancel out, you will get 1 minus v naught divided by e. So alpha is nothing but 1 minus v naught by e. So if the barrier or the step potential is given and the energy of the particle is given, you can find the alpha, and you can just substitute this alpha value in the reflection coefficient and the transmission coefficient, and you can find these values very easily. So question will be directly framed. So let's see the question. Particle of mass m having energy 1 electron volt incident on the step potential of v naught, and find the reflection and transmission coefficient. So particle's energy is given 1 electron volt and potential is given 0.75 volt. So you just put the value 0.75 divided by 1 will give you your 1 minus this will give you alpha, and substitute the value of alpha here. You will get reflection and transmission coefficient. So reflection will be 1 upon 9, that will be 0.11, so it will be 11%. Now r plus t must be 1, so remaining will be 89%. So transmission will be 89%, and reflection will be 11%. So see, this is the case when the particle has the energy greater than v naught. So we are having the transmission is greater than very large probability, and reflection is very small. But when the energy will be less, then you will get the opposite thing, means this will be less and this will be large. So let's see one more question first. So if the wavelength lambda 2 equal to 2 lambda 1, means this is given. After transmission you get this 2 lambda 1 wavelength. Initially we assumed lambda 1 as lambda, and we need to find the ratio v naught by e. So see, lambda 1 by lambda 2 is nothing but h by p1 h by p2. So from here p2 by p1 and p2 we know under root 2m e minus v naught for the 2, because energy is higher, and for the p1 it is under root 2 me. From here you will get 1 minus v naught by e, and you know this ratio lambda by lambda 2. So lambda 1 divided by lambda 2 is nothing but 1 upon 2. So square and find the value of 1 minus v naught by e. So from there you will find v naught by e equals 3 by 4. So these are simple questions will be asked to you, so you can solve them. Now let's consider the second case, that is energy is less than v naught. So when particle's energy is less than v naught, then what happen? Means classically we know if particle has less energy than this, it will be forbidden after this, means it can't move from this. But quantum mechanically we will get something else. So let's see what we will get. So particle, for classically particle will reflect from x equal to 0, and reflection coefficient will be 1, totally reflected, and transmission will be 0 for the classical. Now for the quantum mechanics, what happen? For the x less than 0, this will be the equation you will get. So for less than 0 we will get the same equation, and for the greater than 0, this time you will have e minus v naught. We can just take the minus common, because this time v naught is greater than this, so you get minus sign here. And now we will get assume this thing as k2 dash, because k2 was nothing but that was positive, so k2 dash will be negative. So these are your two equations. Now you can solve them according to the differential equations we have solved. So again we will get d square plus k1 square equal to 0, and d will be plus minus iota k1. So solution will be exponential this. And for same for the second one, this time it is minus here, so it is d square minus k2 dash square equal to 0. So from here d is nothing but plus minus iota k2, not iota, because this time you have minus here, so it is k2 dash. So psi 2 will be c exponential k2 dash x plus d exponential minus k2 dash x. So psi 2 tends to 0. So this is your two solutions, two wave equations, means before the barrier or the step potential and the after potential you get psi 1 and the psi 2. Now see, again we need to find this CD and AB. So how can we find? Before that, let me tell you that after transmission from here, we will see that particles probability will tends to 0, means wave function as x tends to infinity, wave function must tends to 0. So that is the condition we will use here to find this, to solve this. So as the x tends to infinity, this must tends to 0. So if you just push wave function will be 0 at the infinity, we know this condition, so this will be 0, and x equal to infinity, this will be 0, but this will go to infinity, means this must be 0, only then this condition will be satisfied. This condition satisfied only when this term is 0. So that's how we'll get c equal to 0. So for the psi 2 we'll get only this second wave, and for the first one you have these two terms a, b and d. So this time we need to find this a, b and d. So again first you need to find the probability. So probability is nothing but take the psi 1 star and the psi 1, and you will get this, and for the psi 2 star will give you this. So this time you will get again the probability is oscillating for the first reason, the same one, and for the second one you will get this probability. Now see, this is the case, means this time we are getting some probability inside them, means the particle's energy is less than v naught, but still we are getting the probability of finding the particle here. So that is a different thing in the quantum mechanics, that you will find the particle here. So and this probability is decreasing exponentially, means as x is increasing, this probability is decreasing to find a particle inside. So and it is exponentially decreasing. So let's see this probability more. So this is your probability of transmission. So this is your probability of transmission. This is d square exponential minus 2 k2 dash x. Now you can just solve this according to the same means at the junction or the boundary condition that wave function must be 0 and differentiation must be continuous, or the wave function must be continuous. So you can use those conditions and you will again get this ratio. Means you can find the value of d square in terms of the a square. So you will get this equation. So you can solve them just like we solved here and find the value of this ratio of this b by ac by, just like we have find this we can find here also. So this probability will be like this. Now see, when x equal to 0 you will have the maximum probability, means particle at here will be maximum to find here. So at x equal to 0 probability will be maximum and we assume that as p naught. So at x equal to 0 this will be your probability d square, we assumed it as p naught. Now px will be, can be written in terms of, means px can be written in this way. So that's how you can write the px, means probability at any point after this. As x is increasing you can find the probability it is decreasing, and at x equal to 0 probability is maximum, that is p naught. So there is a distance x naught at which this probability will become p naught divided by epsilon. So 1 upon epsilon time p naught, when this will become, that is the distance x naught. So let's find the distance, because at that distance we will see that we'll assume that particles probabilities all completely tending to 0, means that is the case, means we will assume that there is no particle after that. So that is the point as p naught by e. So this px will assume p naught by e. So p naught by e equal to p naught will cancel out, and from here we can just take this e inverse minus 1. So just compare these two terms and find the value of x naught, and that will be equal to 1 upon 2 k2 dash. So this is the distance at which the probability of finding the particles is almost 0. So that is the case. So this distance is depending on many things. It is depending on the k2 dash, and k2 dash is depending on the v naught. So as you increase the potential, this will increase and this distance will decrease, means up to the point at which the particles probability is 0. So that distance is decreasing, means as the potential is increasing, means the probability will decrease to find the particle at the any point. And as you increase the distance from the x equal to that point, so that is also decreasing with the x. So as you increase the potential of the step, then this probability will decrease, and this x increase, then probability is again decrease. So you must remember these two results, very important. Now so you must remember these things and how this step potential works. In the next lecture we will see that, means again here you can say that if there is you have this step potential, and now there is this step potential is removed and you make this barrier, and that distance at which the particles probability to finding is 0 is coming out of it, then you will say that particle can be find it after this barrier also. So that is the thing we will study in the next lecture, that is called the tunneling phenomena, when the particle will tunnel through this, because there is particles already finding out of this also, and this is called the potential barrier. When this step potential become, means it is again 0, then it is potential barrier, and now the particle can be find it outside of this also. So that is how you define the tunneling phenomena. So we'll see this in the next lecture. So I think there will be many doubts to you. So still if you are facing some difficulty, you can just put in the comment section. I will make a short video on that. So I hope it is clear to you. So thank you everyone.